So good morning. Do you like Sudoku? Like Sudoku. All right. So the Sudoku craze has swept the globe. One of the authors played an online game of Sudoku. The graph provides information about how well he did. His time is marked with an arrow. Okay. So we're looking, his rank here is in the top 19%. In this chapter, you'll learn about how to describe the location of an individual observation, like the author's Sudoku time within a distribution. Okay, so we have a definition here. We say the percentile of a distribution is the value with p% of the observations less than it. Note that percentile does not mean percent correct. Also, percentiles are whole numbers. So if you get a decimal, you need to round it to the nearest whole number. Okay, so we have a stem plot here that shows the number of wins for each of the 30 Major League Baseball teams in 2012, with 6/1 represents a team with 61 wins. Find the percentile for the following teams. The Minnesota Twins, who won 66 games. Okay, so we're looking at this one right here. So we are going to count the number of teams that are less than that. All right, so there's 1, 2, 3 teams less than the Twins that year. Okay, so I'm going to take 3 and divide that by the total. Okay, and 3 divided by 10 is going to give me the 10th percentile. Because 3 teams had fewer wins. Okay, the Washington Nationals, who won 98 games. All right. So that's going to be this one right here. And so how many teams were less? Were less than 29 in this case. So 29 divided by 30 should get, put that in your calculator. Well, we're going to say about the 97th percentile. Because 29 out of 30 teams had fewer wins. The Texas Rangers and the Baltimore Orioles, who both won 93 games. Okay, so that's going to be right there. Okay, so if we count, let's see, there's 1, 2, 3, 4, 5, 6 that are higher, and 2 that are equal to 93, right? So that's 8 total. So we are going to say that 22 out of 30 teams had fewer wins. And so what is that percentile? Put that into your calculator.
Wait, so when you have like repeats of the number, you don't count it in the fewer than, right?
You're talking about if they're both 93, that's correct.
Okay.
It's fewer, has to be fewer wins. Okay, what's that percentile? 73rd percentile. Okay, so for percentile, again, it's always less than, and they are integers, whole numbers that we round to. Okay, fairly straightforward. Turn the page for me. All right, and we use percentile and a lot of different things, right? I would take my children to the doctor's office, right, for an annual checkup, or if they're sick or whatever. They'll measure their height and weight. And then they will compare that. They will express their height, for example, as a percentile of all the other children that are the same age and same gender, for example. Okay, so here we have what's called a cumulative relative frequency graph. The table and cumulative relative frequency graph below shows the distribution of the median household incomes for the 50 states and the District of Columbia in a recent year. Okay, so there's two different tables here, okay? So the first one is a frequency table. Actually, there's four, okay? So we have median income in the thousands, so 35 to up to 40,000. There's one in that. Okay, and then there's the relative frequency, which is expressed as a percentage. Okay, so there's 1 out of 52, which would be approximately 2%. And then there's 10 in the 40 to 45. And so the 10 out of 51 gives us approximately 20% out of that. Okay, and then there's the cumulative frequency, which is going to add everything up to that. Okay, for example, in this one, the first one's 1, but this one is 11 because it adds the 1 and the 10 together, cumulative. And then we have 14, so the next one, the 14 is added to that 11, which would be 25. Okay, and the cumulative frequency, relative frequency is expressed as a percent there. Okay, or percentage. And so this is a graph. It says the point at 50,049 means 49% of the states had a median household income less than 50,000. Okay, the point at 55,0.275 means that approximately 72.5% of the states had a median household income less than 55,000. Okay, and so you can calculate how much that increased from point to point by subtracting those percentages. Okay, so let's take a look at this. It says use the cumulative relative frequency graph for the state income data to answer each question. At what percentile is California with a median household income of 57,445? Okay, so we are going to go to, let's say, 57,000, which is somewhere right in there. All right, draw that line. And then we are looking on the left side there. So I said it was about the 78th percentile. Okay, so if you were to see a question like this on the AP exam, most likely it would be a multiple choice, right? And the only reasonable correct answer would be the correct answer, right? If it's free response and you put like the 80th percentile or something like that, that's fine, as long as it's reasonable. Okay, you can't put the 30th percentile or something like that. Okay. Part B says estimate and interpret the first quartile of this distribution. Okay, so let's go to the first quartile, which would be 25%. All right, that means we are looking here on the left side at approximately 25%. So I said the first quartile is the 25th percentile. And it asks us to interpret that. So we're going to say about 25% of the states have a median income, okay, put it in the context of the problem, that's important. So have a median income. Less than. And I said, into the graph. Less than 45,000. Okay. Any questions for me on percentile there? Okay, well, we're going to talk about probably something that you have not seen before, which is called a z-score. And this is a pretty important concept in stats. And so let me explain why we use z-scores. We use them in order to make comparisons. So let's say, for example, that you take the SAT. And we don't care about the English side of that, just the math. Let's say you score, you're pretty good, right? Let's say you score 720 on the math section of the SAT. And your friend takes the ACT. And like I said, we only care about the math. They score 28 on the ACT. Well, who did better? Well, in a sense, we're comparing two different things, right? They are related, but we are comparing two different things. But we can do what's called standardizing in order to make those comparisons, okay? So why do we standardize? In order to make comparisons. So a z-score is called a standardized score. If X is an observation from a distribution that has a known mean and a known standard deviation, then the standardized score for X is going to be Z equals the observation minus the mean divided by the standard deviation. This is also known as a z-score, and a z-score tells us how many standard deviations from the mean an observation falls, and also in what direction. Either above the mean, positive, or below the mean, negative. Observations larger than the mean have positive z-scores. Observations smaller than the mean have negative z-scores. Okay, refer back to example 1. Wins for team in Major League Baseball. In 2012, the mean number of wins for teams in Major League Baseball was 81, with a standard deviation of 11.9 wins. Find and interpret the z-scores for the following teams. The Evil Empire Yankees with 95 wins. Okay, so let's find the z-score. Z is going to be X minus mean over standard deviation. So the Yankees had 95 wins. The mean was 81. So they are above the mean. They have to have a positive z-score. And standard deviation was 11.9. Okay, so put that into your calculator. We have 95 minus 81. And then we divide that by 11.9. And someone help me out. What is it? I got like 1.18. Okay, but it also says to interpret that, okay? So the New York Yankees were 1.18 standard deviations above the mean. And part B, the New York Mets with 74 wins. So my Z-score is going to be 74 minus the mean, minus 81. So they're below the mean. So obviously my Z-score will be negative this time. And so 74 minus 81 divided by 11.9. That gives me negative 0.59. So my interpretation this time would be the Mets were 0.59 standard deviations below the mean. So let's look at another example here. The single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61 in 1961. Mark McGwire hit 70 in 1998. And Barry Bonds hit 73 in 2001. By the way, my grandmother, bless her heart, may she rest in peace, never threw anything away ever. So I have all of my father's baseball cards. I have Roger Maris's rookie card. Yes, I do. Let's go on. In an absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including the quality of the batters, the quality of the pitchers, the hardness of the baseball, dimensions of the ballpark, and possible use of performance-enhancing drugs. To make a fair comparison, we should see how these performances rate relative to those of other hitters during the same year. So this is what a Z-score allows us to do. It allows us to standardize it and then make comparisons between them. So compute the standardized scores for each performance using the information in the table. Which player had the most outstanding performance relative to his peers? Okay, so let's find Babe Ruth here. We're going to find his Z-score. He hit 60 home runs. The mean that year was 7.2 with a standard deviation of 9.7. So what's his Z-score? 5.44. Okay, and so go ahead and calculate the other 3 for me. Can you do that? So check your numbers with mine there. Okay, I got 5.44 for Babe Ruth. Roger Maris was 3.15. Mark McGwire, 3.88. Barry Bonds, 3.91. So we are going to say Babe Ruth had the best performance. Why can I say that? What's his Z-score? 5.44, meaning what? What's the interpretation of the Z-score? It's the number of standard deviations above the mean. Okay. The average number of home runs that year was 7.2, and he hit 60. Okay. He's over 5 standard deviations above the mean. Okay, which I cannot tell you how phenomenal that performance was. Okay, and we're going to look at what that means later on in the course, right? But if you were 5 standard deviations above the mean, that is extremely rare and just indicative of how great a performance that was. Okay? Okay. Questions so far about z-scores? It's kind of important, okay? Let me emphasize this, okay? Because this is what's coming next. You're gonna use z-scores to do something else, but you need to calculate the z-score. Write it down, okay? Set it up. In stats, a lot of times we care about the process of how you get the answer, not just the final answer. Okay, the answer is not just a number at the end, it's the whole entire process about how you get there. Okay. All right, well, turn the page for me. We're going to do one more thing here. It is common to transform data, especially when changing units of measurement. It's important to know how the transformation affects the mean, the median, and the standard deviation. Okay, so we're going to look at 2 different scenarios here. Okay, the effect of adding or subtracting a constant. Adding the same positive number or subtracting that from each observation will change the center and location, but it does not change the shape of the distribution or measures of spread. Okay, that is the important thing to know. However, multiplying or dividing by a constant, when we multiply, it changes the measures of center and the location. It will also change the measure of the spread. It does not change the shape of the distribution, however. Okay, and so the example that I use to kind of explain this, and I think this makes sense intuitively if you think about it. Let's talk about grades. Let's say, hypothetically speaking, okay, the average on our first test was 80. And the supreme stats dictator, out of the generosity of his heart, decides to give everybody, this is hypothetical, 10 points. What will happen to the mean? It will go up by how much? By 10 grade points, right? That makes sense, right? Let's say that you scored 75 on the test. So you were 5 points below the mean before I added 10 points, right? And so now you have an 85. How far are you from the mean? 5 points. I said 5, right? So here's what happened. Look, okay, let's say everybody's test score is between my hands here, and I add 10 points. So what does it do? It does, boom, it does that. But it doesn't change how far spread out the distribution is, right? Does that make sense? So if I add or subtract a constant to a distribution, then the measure of center and the location will go up. That makes sense. However, the shape will not change because everything is changing by the same amount. And the spread will not change either because everything is changing by the same amount, a constant. That's if I add or subtract. However, if I multiply or divide, let's say that I take everybody's test and I double the score. Now we're into the realm of fantasy, right? Let's say you made a 30 on the test and I double it. And so now you have a 60. Your test grade would went up by 30 points, right? But another person made a 40. I double that. Now they have an 80. How much did it go up by? By 40, which is not the same as what the other person did, okay? So if we multiply or divide a constant by a distribution, it will change the center and the location. It will also change measures of spread, the range, the IQR, the standard deviation. However, it will not change the shape of the distribution. Okay, so let's look at an example. Here's a graph and a table of summary statistics for a sample of 30 test scores. The maximum possible score on the test was 50 points. Okay, so here's my distribution. What's the shape of the distribution? Probably less skewed, right? That's what we want. We want a left skewed distribution on test scores, not a right skewed distribution, right? So here's the summary statistics. Total number of test scores. We have the mean, standard deviation, minimum. Woo, okay, and then Q1, median, Q3, max, IQR, and range. Suppose the teacher was nice. Not true. I'm not nice. And added 5 points to each test score. How would this change the shape, center, and spread of the distribution? Here are graphs and summary statistics for the original and the +5 scores. Okay, so look at the distributions. Here's the score. Here's the score +5. Did the shape change?
No.
No, the shape stays the same. Did the center change?
Yes.
Yes, the mean increased. Where's it at? X bar. Okay, so look right here. The mean of the first was 35.8, and the mean of the second, it increased by 5. That makes sense because everything went up by 5. So the center increases by 5. And the spread, look at the spread. Well, it stays the same. Because everything is changing by the same amount. Suppose that the teacher in the previous alternate example wanted to convert the original test scores to percents. Because the test was out of 50 points, he should multiply each score by 2 to make them out of 100. Here are the graphs and summary statistics for the original scores and then the doubled scores. Okay, how did the shape, center, and spread change after being multiplied by 2? Okay, well, look at the shape. I have a left skewed distribution and the new one that is doubled, the shape is also left skewed, so the shape stays the same. Okay, what happens to the center? All right, here's X bar. The original was 35.8. The new one is double that. Okay, so the center is multiplied by 2 for this one. And what happens to the spread? Look at the standard deviation there. Okay, spread is also multiplied by 2.